This is part 2 of chapter 8.2. Last time we left off with sample proportions, and then we talked about this idea of simulating kind of what would happen if we increase sample size with a number with 300, doing 300 samples of different sample sizes, what would happen. And here are the key points from that last example we did. The first thing that we want to take away here is that first word here that we want to put in there is called shape. As the size of the sample n increases, the shape of the sampling distribution of the sample proportion becomes normal. This becomes very important. This idea of normal, we need this, right? This normal, this allows us to use the normal model. You know, the normal curve, but again, I'm using that word model. The normal model, right? It allows us to use that normal calculator to solve problems. The second big takeaway, key point, is the idea of center. The mean of the sampling distribution of the sample proportions equals the population. And so that's an important idea. And so you can see that gets summarized below. But what we're talking about here is that p hat, right? The mean of all those p hats is going to be equal to p, which is the population proportion. And then the last piece is spread. The standard deviation of the sampling distribution of the sample proportions decreases as the sample size increases. Very important point there. And you can see, as we had, this is n equals 10, it's more spread out. Here, n equals 100, and so it's not as spread out. They're very close together. And that's what we're talking about on this problem. And so we have that conclusion there. And then we have kind of the big idea of this section, sampling distribution of p hat, the sample proportion. We do it multiple times. And so we have to kind of keep these things in mind here. The shape of the sampling distribution of p hat is approximately normal provided that this is true. So we're going to have to check that. So when it says in some of the problems, what's the sampling distribution, we need to make sure that this is true here. The other conclusion that's important, of course, is that here p hat, right, the distribution of p hats equals the population proportion, which we had said here in center. And then we have this formula right here that we need to use. It is the standard deviation of the sampling distribution. We're going to calculate that so that we can then use the normal model. And so we're connecting this here in the previous problem. This is similar, that n needed to be greater than 30. For the sampling distribution of the proportion, that was for means, right? For the distribution of means, n needed to be greater than 30. Here we have a tougher condition to meet. N times p times 1 minus p has to be greater than or equal to 10. And so the last idea is the model on the previous slide, which we were talking about, requires that the sampled values are independent when the sampling for finite populations, right? The assumption is verified by checking that the sample size is no more than 5%. So not only should it be big, though, the sample size also needs to be less than 5% of the population. So it's a very technical stuff, but we want to make sure you're aware of that. Example 2, let's take a look then. What do we got here? Based on a study conducted by the Gallup organization, 76% of Americans believe the state of moral values in the United States is getting worse. Suppose we obtain a simple random sample, n equals 60 of Americans, and determine which of them believe the state of moral values is getting worse. Describe the sampling distribution of the sample proportion of Americans with this belief. So to describe the sampling distribution, we first need to make sure the first condition is met, right? We want to look at our first condition. We want to make sure if this is a normal distribution, this condition needs to be met. So we want to check n times p times 1 minus p. Is it less than, is it greater than or equal to 10? So then we would do that calculation real quick. So you end up with 0.60 times not 0.60, it's early in the morning. N is equal to 60 times 0.76 times 0.24, and you get approximately 10.9. So this is bigger. First condition met. Second condition met. One of these other conditions here is that the population needs to be less than, the sample needs to be less than 5% of the population, and so that second condition definitely met, right? N equals 60 is less than 5% of the U.S. population for sure, right? There's millions of people, so we're met right there, and so now we know we have a normal. We have a normal distribution right here. Again, it comes from here. Where are we talking about this here? The reason, again, the sampling distribution becomes normal, right here. As the sample size increases, the shape of the sampling distribution of the sample proportion becomes approximately normal. As long as we have these conditions met, we have a normal distribution. Why is that important? It's important, again, because that allows us to use the normal model. And so what do we know? We know P is equal to the distribution of the samples, which is going to be equal to 0.76. And the one calculation that needs to be made is the standard deviation of P hat, which is the square root of P, 0.76 times 1 minus P, 0.24 divided by the sample size N, which is 60. Put that all together and you should get 0.055. Always check my math. I've been known to make some mistakes here. And so that's our distribution there. Let's go on to example 3. Let's do A. In a random sample of 120 Americans, what is the probability that at most 12% have hearing trouble? At most is a key term. So really what we're calculating here, go back to chapter 8.1, 7.2. Probability that at most 12%, probability that P, right, the probability that that P at most 12%, right? The sample that we do when you sample 120 is at most. At most means less than or equal to 120. So we're looking for that. Now that notation is a new notation. In the past we had X bar or X. And so now we're looking at that. So how do we get that answer? To get that answer, we need to know, we need to use the normal calculator. And then, but to do that, we know the mean is going to be, right? We need the mean of the mean of P hat is going to be equal to 0.12. And then what we need is the standard deviation of P hat. And so we need to do that calculation here. The standard deviation of P hat, it's the square root of let's repeat that again. This is not 12, this is 15 here. That's the P hat, or that's what we're our P. And then so it's 0.15. 0.12 is what we're going to and I don't know where I got 120. I'm all messed up here. This is not P hat. P hat is at most 12%. So that's 120, 0.12. I got the 120 because the numbers are similar. Suppose a simple random sample. So it's 0.15 times 0.85 divided by 120 in this case. So that's what we need, that value there. And when you get that value there, it looks like we get, what is that answer? I got to do that calculation. So this calculation turns out to be 0.032, let's just keep a few, so 59. Okay, so that's the standard deviation. I forgot to check those assumptions like we did on the top here. We surveyed 120 Americans, so that's for sure less than 5% of the US population, since that's who we were talking about, Americans. And then that other value was important. We needed to check here. Let me do a different color. We needed to check that N 120 times P times 0.15 times 0.85. We needed to check that that is greater than or equal to 10. So again, we always need to check that to make sure we can use the normal model. And so you get 15.3, which is greater than or equal to 10. So we're good there, and now we can use the normal model, which we're going to do here. So what is the probability that the proportion, the sample proportion, is less than or equal to 0.12, at most 12? We go to our normal calculator. Stat calculator is normal, right? We end up with a normal calculator. What are we going to put in here? The mean was 0.15. The standard deviation was 0.03259, which we got back over here. And so then we can now calculate that it's less than 0.12. Compute, and I get my answer here, 0.179. So our answer here is, let's change color, 0.179, and we got that from the normal calculator. So that was part A for us here. Now moving on to part B. Suppose that a random sample, same thing, 120, listen to music, and the results, this using headphones results in 26 having hearing trouble. What might you conclude? Well, I'm going to calculate p hat first. 26 out of 120. What is 26 out of 120? It's 0.217. So we get 22% of people have hearing loss. Is that unusual? Are these headphones bad? Because now we know 12%. So what's the probability? What's the probability that 22% of people have hearing loss when it's only 12% of the population have it? So we're just going to go ahead and do that calculation here. All we need to do then is find the probability that p hat is greater than or equal to 0.217. That's what we're going to do. So same question here, same exact math. And so we're going to go ahead and just do that calculation. Everything stays the same. You're going to put in here 0.217 greater than, and so what's the probability? Basically 0.019, 0.0198, 0.02 if we round that number. So the answer we get here is 0.0, I already forgot. It is 0.02, 0.02. Or basically a 2% chance that this would happen. What can we conclude? Maybe those headphones are bad, right? We don't know, we need to do further testing, but this probability gives us a clue that that might be the situation.